Hey guys, your boy Chili. Welcome back to Hardware 3D Tutorial 47 Part 2. To recap, in Part 1 we focused mainly on theory, Gaussian blur and separated filters. In Part 2, we're going to see how that is implemented in code with a multi-pass post-processing flow. We're then going to make things dynamic with ImGUI controls that'll let us tweak various filter parameters at runtime, play with them, see how they change the output right before our eyes. Finally, we're going to add downsizing and upsizing to the mix, realizing a pants-pooping 16 times performance increase. And as a bonus treat at the end, we are going to play with the graphics debugger a little bit. We're going to take a little look under the hood of all of our post-processing GPU work. So in the code, I create a class called BlurPack, and it just contains a bunch of logic and data required to handle our blurry stuff, our Gaussian filter. So, well, first of all, in chilimath.h, I create a little function here called Gauss, and this just calculates the normal distribution for a value of x and for a sigma. So the mean is set to be 0. You can see it's 1 over the square root of 2 times pi times sigma squared times exponential function of negative x squared over 2 times sigma squared, which again is this function here when you set the mean to 0. It's just this function here. What the BlurPack does is, well, it stores a constant buffer for the kernel, and it stores another constant buffer called control. And it's just a bool to tell the shader whether we're doing a horizontal pass or a vertical pass. The kernel pixel constant buffer controls as an array of XM float 4s for the coefficients, and it also stores the number of taps, so the width of the kernel. So you can't just have a dynamically sized array for this thing. You got to pick the maximum that you would want to store in this constant buffer. So I set the maximum to 15, but I have the option of telling the shader that we're not using all 15 of these. You know, maybe we're only, our kernel width is only going to be 7 or whatever. And the other thing here is, in HLSL, and this is a tricky thing, but you can't have an array of floats. Your arrays have to be the size of float 4. This just has to do with the alignment and how HLSL addresses things. So even though our coefficients, we only need one float, for alignment purposes, we have to use 4 floats for every coefficient. And we just leave the other ones unused. So we're probably just going to use the X component, I would guess. But yeah, we got these 2 constant buffers, and then we've got some functions to set the kernel, you know, given a radius and a sigma value. We set all those coefficients. And the idea is very basic. You got a for loop, it's got I, the radius, let's say this 1, 2, 3, 4, 5, 6, 7, right? So I don't know, if the radius is 3 in this direction, 3 in this direction, then I starts off at 0. X is equal to, you know, I minus 3. So we'll get negative 3, negative 2, negative 1, 0, 1, 2, 3. This is your X that you pump into the Gauss function, and that gives you your coefficient. And you just loop through I, going through the entire kernel there. That gives you your coefficients. Now, we want to normalize everything so that when you add all the coefficients together, their total should equal 1. So what we do is, when we're creating those coefficients, we take the sum of them all, and then at the end here, we divide each coefficient by the sum of all coefficients, and that means that their total sum will now be 1. So there you go, we generate our Gaussian kernel coefficients here. Very nice function. We can just call it with very simple parameters, and it does all this annoying loopy work for us. And then we can have functions here to set it to do a horizontal pass or a vertical pass, which just sets that control constant buffer to true or false. And we have a function here to bind, which will bind, you know, the kernel constant buffer and the control constant buffer, and it binds this shader, which is our blur pixel shader. So now we look at our blur pixel shader. It's obviously going to be quite a bit different because now it's using the constant kernel buffer to read in coefficients and multiply them. So if we look at the shader here, we see I've added a new shader called blur outline pixel shader, and that's just our blur that we had previously. So this is the one that takes the max color. Now we've got a new one, which is just blur pixel shader. And this one is using our Gaussian technology. So we've got the two constant buffers in here. Note that we're declaring it as an array of floats, even though it's going to occupy 4 floats for every element here because of padding. And so the first thing we do is we determine again our dx dy, but this time the dx and dy changes depending on whether we're doing a horizontal or a vertical pass. So if we're doing horizontal, our dy should be 0. We don't change in the y direction as we loop over our kernel. Kernel only moves left to right. And if it's a vertical pass, kernel only moves up and down, so dx is 0. And again, we loop through I. We do similar things. We have to look our coefficient up in our array, get the coefficient, then we multiply the sampled pixel in the input texture times the coefficient. We accumulate that and we return that value at the end. No need for division. That's already taken care of by the coefficient. So we've got this thing here for our blur, and we got our blur outline. If we look at the frame commander, we see that we're not using the blur yet. We're not using our new Gaussian. But we can see here, at least we've developed the blur pack. We've developed a blur pixel shader here. And in the next commit here, we actually implement that. So in the frame commander now, we actually need 2 off-screen render targets. We need 1 render target to render to for drawing the original outline. The second render target we render to when we do the horizontal pass. And then when we do the vertical pass, we render to the swap chain. Going down here, we can see what do we got. So the pixel shader, we remove that from these full screen shaders because that is in the blur pack now. We also remove the full screen blender. For some reason, I believe in this one, we're only going to do a blur filter. We're not going to do the outline filter here. Yeah. So we're just testing our kernel and everything with a simple full screen blur. So we remove all these, masking stuff and outline drawing, and we just do full screen blur horizontal pass, followed by full screen blur vertical pass. So render target 1 is the input, render target 2 is the output. We bind the blur pack, we set it to horizontal mode, we draw, then we bind the swap buffer, bind render target 2 as the input, blur pack is set to vertical mode, and we draw again. That's fair enough. And in blur pack, I just change here some defaults. Default radius is now 7, and the sigma is 2.6 default, and some adjustments in the loops here. I guess I was off by 1 or whatever. Not a big deal. We needed to add some padding in here for alignment purposes. And when that is all said and done, here's what you get. Here is our scene with a full screen blur, but Gaussian blur, not box filter blur. And I know it might be difficult to tell, especially without a side-by-side, but I do believe that this is a higher quality blur than a simple box filter can give you. Looks like it's doing its job quite well, at least as a blur filter. Now the next step is to make things a little more dynamic. We've got these constant buffers. We can change their values from frame to frame. So what I did was for the blur pack, I added a window. We got a slider to change the radius and a slider to change the sigma of the kernel. In frame commander, I add a function show windows, and that will call blur.showWindow. And in app.cpp, we call frame commander.showWindows, and that'll show windows for any, parameters that the frame commander might want to expose. And if we do that again, we have our scene here, and we can change the radius of the kernel. Notice that if I turn the radius up, it doesn't actually make it much blurrier, because even though the kernel has a higher radius, the sigma, which is the shape of the bell curve, even if I increase the radius this much, it's not going to do shit because the sigma's down here. It's only if I also increase the sigma that changing the radius will make a difference. On the other hand, if I keep a very narrow radius but increase the sigma a lot, it's going to look like this. It's going to start to become close to a box filter. So there's a balance between increasing the radius and increasing the sigma. So I turn the radius up. Now if I turn the sigma up, you can see it getting blurrier. But if I turn the sigma way too high, it actually becomes more like a box filter. On the other hand, if I turn the radius way down, turn the radius down to 2, it doesn't matter how high I turn the sigma up, because it can only ever blur to a radius of 2. It's only reading 2 pixels away from the base position. But there you have it. There you have your controllable blurring with Gaussian sexiness. I don't know what to say. Doesn't matter. It looks cool, don't it? Could be like a cool effect that you use in your game. Who cares? Moving on. I now allow you to control your filter type. So I've added 2 functions. Here I've added a function, where is it? So I've added set kernel box. So if you call set kernel box, it will set the kernel values as a box filter, meaning all the coefficients will have the same value, as opposed to having a value according to the normal distribution. And then up here, we just have a bunch of, nasty ImGUI code for selecting something. So it's, where is it? It's a selectable, where is it? Begin combo. It's a combo box. And you give selectable options, and it's just dumb ImGUI code. It's not really the focus of this tutorial. So now you see we've got our situation with a radius of 7 and a sigma of 2.6. We change this to a box filter, and it becomes box filtery. Gaussy, boxy. All right, so we got our Gauss blur working nice. The final stage is to use that for the outline. So we change the blur outline pixel shader to use our kernels and our stuffs and our things, horizontal or vertical, dx, dy. Yeah, we know this. Instead of looping through x and y, we just loop through I, look up our coefficient, and here we do our alpha. So we multiply only the alpha by the coefficient, and we do our max of the other things. So it's the same idea as blur outline before. We do max of the color channels, and we multiply the alpha times the coefficient, recompose them at the end. In blurpack.h, for whatever reason, I allow you to pass the shader name in through the constructor. I don't know why I figured that was necessary, but I did it. It's a thing I did. And then down here, we need the blender again, because we're going to be composing the halo over top of the original image. Outline masking and drawing passes. And then full screen blur horizontal, full screen blur vertical, plus combine with the original image. And Bob is your uncle. She looks good. She looks fine. I nearly lost my mind. It's all good, right? We can crank up the radius to 12. We can crank up the sigma. We get our nice, beautiful effect there. Or we can change her down to boxy town. Get our boxy filter. It's all good. All right, so we got separable filters, Gaussian. It's all working with the outline. Everything's good. Time to end the video, right? Now, actually got one more thing to throw at you, a little bit of additional optimization for this technique here. A little bonus part to this video. So let's just crunch some numbers here. Let's say, for our argument's sake, our output, it's got 1 million pixels. We're working with a 1 million pixel resolution. All right, let's say the radius of our kernel is going to be, I don't know, let's say 10 pixels. So that means the width of the kernel, 21 pixels. All right, so how many pixels do we sample to do our kernel? Well, that is going to be, 21 times 1 million times 2. So about 40 million pixels sampled to execute this shader. All right, can we do better than this? Well, yes, we can. Let me tell you one very simple, very forehead way of doing that. What if we were to make our window, our output, half as wide, half as tall? Well, then the number of pixels would be divided by 4. So we'd only be looking at 250K. So we'd do 1/4 of the work. Now you might be saying, Chili, reducing the resolution that's not that impressive. Well, here's the smart thing. Normally, you reduce the resolution, your game looks worse. But what we're doing is we're blurring an outline. So normally, if you reduce your resolution and then you were to scale it up to the original window size, so take this reduced resolution, scale it up. So what happens when you take a low res thing and you scale it up using bilinear interpolation? It becomes blurry, which usually looks gross. But what are we scaling up with our effect? We're scaling up our outline that has been blurred when we scale that up with bilinear filtering, what happens? Our outline becomes blurrier. Oh no, we just did the thing that we wanted to do. Only we run our kernel over 1/4 the amount of pixels, so our work is 1/4 less. And it gets even better, because here, to get a radius of blur of 10 on your normal image, you would need a kernel that is 21 wide. Well, if you did that same blur on a reduced image, you would get a blur radius of 10, but then when you size it up, your blur radius becomes 20. To get that same amount of blur without the resizing, you would need a kernel that is, like 41, which means your work would go 4 times up. So you save 4 times the work by working on a smaller thing, and you get 4 times more work by upsizing your blur. That's a 16x performance for cutting your working resolution down by half in both directions. 16 times performance bonus. Is that not kind of cool? So what's the thing? What do we do? Well, it looks like we only have to change one file, the frame commander. And what we do is when we create our working render targets, our off-screen boys, we create them with the width and the height divided by 2. And that's it. So we render the silhouettes to this one. They're rendered at half the resolution. And then we do the horizontal blur pass to this one, half the resolution. And then when we do the vertical blur pass, we do it to the swap chain. Yeah, we bind swap buffer. And because the swap buffer is twice as large, it is going to upscale. And as long as we have our texture sampling set to use bilinear filtering, when it upscales, it's going to upscale it nice. Now it says it doesn't work, so that means that I probably forgot something, right? Let's see what it did. Okay, so we're missing the outline. It's kind of weird. Look around. Whoa, what the hell is going on here? This is unacceptable. So something went wrong, obviously. It said so right in the commit. I just saved that commit there to show you guys the ramifications of doing it wrong. So in order to do it right, basically what I'm going to do here, in render target, I'm going to store the width and the height as separate variables. And initialize them in here in the constructor. And then when you bind as render target, we're also going to configure the viewport, because the viewport requires the width and the height. So if we're binding different render targets and they have different sizes, we've also got to adjust our viewport every time we bind. So we're going to change render target so that it adjusts the viewport when we bind. And now we don't have to configure viewport in the graphics constructor. We're now doing it every time we bind a render target. And here we are. We're back in our scene here, and we have got this going with the downsizing and the upsizing. Now there's actually something wrong with this. If I look in close on my monitor, I can notice it, but I don't know if it's going to come through in the encoding in the YouTube. But the upsizing is looking kind of blocky, and the reason for this is when I do the final pass, the sampling mode that I'm setting, it doesn't have bilinear filtering. I fix that later on. Maybe I'll show you guys. But yeah, bilinear filtering isn't working. So this upsize is actually just using point filtering, which isn't as nice. It's obviously not going to be as smooth. It'll become noticeable if you actually do even more reduction. So maybe we'll see that in a future commit. But yeah, we fix the viewports. And here is where we fix that thing I talked about. So sampler full point. So we use point sampling for our blur pass, our horizontal blur pass. But for the final vertical pass where we do the upscaling, we change it to a filter that uses bilinear filtering. So this second true, I believe this one is for mirroring, and the first one is for using bilinear filtering or not. And you can see here for the horizontal pass, we use the point sampling, and for the vertical pass, we use the bilinear. So now if you were to compare this to that previous one, you're going to see a lot smoother. It's a smoother feel on that outline. Here I crank the radius way up so you can see it a little better. But if you compare this to the previous one, and this one is a lot nicer, you can't really tell that it's been rendered at a lower resolution and then upscaled. It's not noticeable at all, and the performance benefits are huge. And here we have made it to the final commit for this video. And all I do is I allow dynamic controllability of the ratio of upscaling. So I replace the divide by 2 with the divide by down factor. And then in show windows here, I do ImGUI begin for blur. Blur pack, instead of doing its own window, it just renders widgets for its own control. And so now the blur pack widgets are just rendered inside the same window as we render this slider. This slider is going to control the downsizing factor from 1 to 16. And we just, whenever it's changed, we recreate those off-screen surfaces. And here we have it, my final form. So we're looking at Gaussian filter with a radius of 7, not bad. At downscaling factor of 1, turn that to 2. Oh, we get much more radius. It's doing less work and it's giving a bigger blur. Crazy. 3, still looking good. It still looks great. There's nothing wrong with this effect here. Try 4. Yeah, it still looks good. Let's try 5, 6. Okay, it's starting to get a little weird. Like if you start looking up, this is 10. We're now rendering at a resolution that's 10 times smaller, and then upscaling that. You're starting to lose information at this point, so it's getting kind of funky. But in like the 5, up to 5 maybe, it's perfectly fine. 5 times reduction of resolution, and I don't even know how much reduction in work that is, but it's a lot. Now, it's a little weird. I'm gonna give it that. It's a little weird. Like if you zoom in, you see some weirdness here. And that's basically these scan lines here crawling, and they're having a huge influence on the outline because, you know, the outline's being upscaled by so much. So depending on your use case, 5 might be too much for you. But let's try 3. I mean, 3 seems okay. It seems pretty good. And one more thing is that it can actually be better if you enable anti-aliasing when you render the outlines. It's not going to crawl as much. But even just 2 is already a huge improvement in performance. And it's the quality is comparable to doing it at full resolution. It's beautiful. And now, finally, the whole reason we did this was so that we could do outlines for all our Sponza stuff. So let's take a look, let's try to find some. Yeah, this geometry renders great. Yeah, let's find one of our pillars. The pillars are rendering perfect now. Beautiful. You can't get a more beautiful outline on this pillar. It's impossible. It's not possible. It's the beautiful, amazing world of whatever you want to call this bullshit we got going on here. It's cool stuff. It's cool stuff. All right, so for you cool dudes who stick around to the end of the video, I'm going to show you a little treat here. So we got our effect. We're just enabling it for the cube here. And now what I'm going to do is I'm going to capture this frame. And let's take a look at this in the graphics debugger, because I don't spend enough time in the graphics debugger. I'd like to show you guys a little bit more of this. It's a great tool. You got to learn to use it by using it though. And honestly, that responsibility is on you guys, but I think it's good to show you guys it, show it off a little every now and then to you guys. So, draw index, we're drawing a whole bunch of bullshit here. There's a light. There is one of the cubes. So this is going to be the pass that draws all the normal stuff, right? So our pass that we're interested in, this is probably going to be stuff for ImGUI, right? Yeah. So we're not interested in that. We are interested in the passes that are doing our crazy effects. Ah, here we go. Okay, so now we're getting to the interesting stuff. So here we draw the second test cube, I believe. Yeah. Just its normal drawing. And then in here, I don't know, we're drawing something, but I can't see it. What about here? Ah, so here we draw the outline of our cube boy. And if we look, render target view, let's look at the object. The resource is object 29. And here we can see, yeah, it's alpha, except for where it's at here. And if we look, the width and the height, 1280 by 720, because I didn't turn up the slider on that bad boy. So that's not doing the reduction. I'll have to show that after this. But yeah, we see our bad boy here. The next pass, we can see it has 6 vertices being drawn. That's a full screen. That's a full screen textured quad if I ever saw one. This should be our vertical blur. And you can see it's gotten fatter. If I zoom in here, you can see, you can't see. What do you mean? It's supposed to be blurred. No, because remember, we're using max on this bad boy. We're only blurring the alpha channel, but the color remains the same. So we have to look at this bad boy with the alpha channel. Take a look at the render target view. Take a look at the underlying resource. We zoom in on this bad boy, and you see it. You love to see it. It's got that blurriness there, but only in the horizontal, not in the vertical. Yeah, you can see barely any blurring happening in this vertical plane, but lots in the horizontal. Then you look at the next pass, and it has recomposed that onto this scene. So it did the vertical blur and composed it on here all in one shot. We're going to do that again. This time we're going to leave both of them enabled, and we're going to turn the down factor up. And I press print screen. Let's take a look at that captured frame, shall we? So here we render the second cube, normal stuff. And here, I don't know what this one is. And here, I still know what that is. But what about this one? Ah, here we go. We've rendered one of our cubes, its outline. And if we look, this time, if we look at the render target view and the object, we see 426 by 240. So this is rendering at a reduced resolution. So we render the green boy at a reduced resolution. We render the red boy on top of him. We do the blur, does it in the horizontal, and it blurs the alpha, and it takes the max of the channels. And when you take the max between the green and the red, you get green and red, which is yellow here. And then you do the vertical blur, and you recompose it back onto the original image. Again, just another little demonstration of how you can use the graphics debugger to really look into how things are working as you are learning. It's not just for, figuring out problems and fixing them. It's also just for figuring out how shit works. Tools, the thing that separates us from, most animals, use them. But that's going to about do it for today. In the next tutorial, we're going to put on our software architect hats again, and we're going to upgrade the frame commander to a modular render graph system. This system is going to compose render pass objects. These objects are going to be self-contained, automated, and reusable objects that encapsulate the idea of a render pass. And the render graph is going to track the relationships between these objects. It's going to diagnose dependencies between them. It's going to be some real cool shit. And I can't wait to introduce you guys to it. But until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button, helps a lot. And I will see you soon with some more Hardware 3D.